Yeah. So let's start today's class. So today we will basically see how one can, by using computer, can solve for fixed points to find if one desire to find any fixed points and the in orbit points. How can one do so with using a computer by using graphical method that we have uh, learned in the previous class. So what else we have done in the previous class? So we have learned that what does a fixed point means, how can we define a fixed points. Then we have further extend the definition of fixed points to say that if we can define the n periodic points in terms of fixed points. So suppose if a point, suppose x0 is a fixed point of the nth iterate of the function f, that means if I applied f n times, the x0 return to its initial value. So x0 become a fixed point that remains fixed under the action of fn, which is nothing but if I use the n times iteratively f, or if I n times composite of m n f. So that is a fixed point. And if I see from the another perspective, so suppose if anyone see that x0, we apply x0, we apply f on x0 n times, and it travels through many other points. Suppose from x0 to it goes to x1, then it goes to x2, x3, and so on so forth. It goes to again x0. So that means it travel in between n many points. So you can think like that the whole trajectory of x0 under the f is the repetition of the sequence. Suppose here for the 2 orbit case, you can see that the orbit is the repetition of these 2 points from x0 to x1, then x1 to x0. So this repetition continues infinitely. So for the n orbit points, if I apply f successively, so in the orbit of x0 under f, we will see that infinite subsequence of x0 to xn will appear repeatedly. So that's why we are calling it a periodic orbit whose period is n, why n? Because after n times it came to its initial point, it repeat itself. So then we have learned that since to know whether a point is fixed point, or whether there exists a point in the domain of f which is a periodic point or not, and if it is a periodic point, what is its period. And now another thing is what will be the fixed points of this function of this map. So for these reasons we want to know what is the fixed points or this. Now we know that to know that fixed points we have to solve an equation. Like if I want to know what is the fixed points, fixed point of n iterate of f, we have to then solve this equation. So if there exists a x, suppose x, which satisfied this equation, we call this x is a fixed point of fn, since this point remain fixed under the action of fn. And we have seen that for the case if we have simple, suppose logistic equation, it becomes very hard to solve the equation by hand. So you can see that f of x is mu into x into 1 minus x. Now what will be the f square x? That will be mu into, since this is nothing but mu into f of x 1 minus f of x. This is mu into fx, means x 1 minus x, and this is 1 minus mu x minus x. So this will be mu x 1 minus x, and this is 1 minus mu x plus mu x square. So if I write it in this way, mu x into mu x square so first is mu x, then mu x square plus mu x cube minus mu x square plus mu x cube minus mu x to the power 4. So it looks like mu x minus 2 mu x square plus 2 mu x cube minus mu x to the power 4. This is if I iterate 2 times by f on any point x, this will look like f square will be mu x minus 2 mu x square plus 2 mu x cube minus mu x to the power 4. Now we know that to find the fixed points here, if we can calculate the fixed point, what will be it? It will be 2-point orbit. So since it tells that the fixed point, by definition will say that the fixed point will remain fixed under the action f square. That means if I repeatedly iterate that point by f 2 times, then from x0 to it will go to some other point x1, and then x1 to it will again return to its initial point. So it looks like a if I say a pendulum, if I what does we mean by the oscillation or periodicity, that it will after some time it will repeat where it was previously. And if you say in case of population, if you see here, we know that the every iteration is like a generation. So it means if I wait if I wait 2 generations consecutively, we will see that the population size will return to its initial state. So you can say the size of the population is oscillating. So that is the thing. So now then to find that point, which point is oscillating, means if I want to calculate what is the value of x0, if x0 is the representation of the population size of any point. So what is the point of x0? If I start from that population size, suppose we have a population of some bacteria, then what is the initial population size of that bacteria? If I keep them and observe its so since here is not a good example for bacteria, because the bacteria's population growth is rather continuous rather than discrete. So suppose some insect population, x0 represents of insect population, and since we are representing the population size of the insect or the reproduction by map, in principle it means that it has a preferred reproduction season. So if I now consecutively, this means if I consecutively wait, here the reproduction is nothing but f. So if I apply f on x0, so it will go to some other state in the next generation. If I measure the population size in the after the next generation, we will see that the population size will change to x1, and then again if I see in the next generation, we'll see again that x1 will become x0. So we'll say the population size is oscillating after every 2 generation. So here these two says you about the time, or that's why this x0 is called the 2 period orbit, because its period is 2. Is it Subhusaji, is it clear, right? Huh. Right, right. Huh. Huh. Yeah, yeah. So that's it. Now here it is. So to find that point, we have to find solution of this equation. So we know only the left hand side of the equation, how it looks like. So left hand side looks like horrible, so it looks like mu x minus 2 mu x square plus 2 mu x cube minus mu x to the power 4. Now we have to solve this equation when f x square x will be equal to x. So I have to find a x which satisfies this equation, because f square x is this, so I retain nothing but this. It should equal to x. If it satisfied x, if I calculate such if I determine such x which satisfied this equation, that x will be the 2-point orbit, is 2-point orbit of the function. Now if I go back to that example, now I want to solve this equation. So this, for you can see, for r equal to 3 there is a solution which will there is a oscillatory solution whose period is 2. So for r equal to 3, or it will be rather mu equal to 2, for we know that mu equal to 2, we have a 2-point orbit of the f. Now let me use a code which I will run in Python to why is my code okay. Okay, let me okay. हाँ हम्म हम्म it is 2 period orbit. It is 2 period orbit because I need 2 time step to reach back in my initial positions. So it is a 2 period orbit. One period orbit look like that if I stay here for all the times, that will be a fixed point. That will be 1 period orbit. So if you think that f square means this is a map. Suppose this is a map. F square is a map. Suppose if we consider f square is some function g map, then any fixed point will look like the 1 period orbit, where I need no extra time to get back to my initial state. Is it clear? Okay, what is going on here? I will say you that what I'm doing here. So first of all, how will solve this? So as we know that we have learned that we can solve it through graphical method. So for mu equal to 2, what I will do, I have to solve this equation. So what I will do first, along the y axis I will first draw f square x, which is f square is nothing but this left hand side, that mu x minus 2 mu x square plus 2 mu x cube minus mu x to the power 4. So first I will draw this, then suppose it will look like something like this, I don't know, something like this, and then I will draw the right hand side in the same axis. So first I am assuming that y equal to f square x, then I drawing this curve. So this is y equal to f square x. For each and every value of x there is a value of y, and the value of y is f square x. Then I will draw so I don't know it will carve 4 point or not, but let's assume that. So and then I will draw up a line which will represent y equal to x. Now where these 2 points will cross each other, their cross sections, or their where they will cross each other, they we will call this is the point where these for same x both of these two equations will satisfy. So I will get then f square x equal to x. So basically here in the code I will this is simple code, I am doing nothing. So first of all I have a means if I write here, it is suppose now to do so I have a x which takes I contain in the x value. So I have taken, I take the grid size very small, so I take 0, 0.001, 0.002 like so, and I continue this series and I take it from 1. So this is my x values, and for each and every x, since I know mu, each and every x I will get a value for f square x. If I put this value, if I put f square 0.001, I will get something. I will put that y, and suppose x is here, x is 0.001. If I put the value in f square, I will get a point here that will corresponding to f square 0.001. I will put the point here. So that's where that's the way I will generate this card. And again similarly for x equal to 0.01, where the y equal to 0.0, and then I'll put a point, and that's why we'll got this line. So that is doing here in the code. So first we have defined that function. So I have to, this is mu means we'll solve for 3.0. So not 3.0, maybe 3.5. Let's play with this mu, and this is x into 1 minus x. That is basically a logistic equation. Now I am saying whether where is the solution. Okay, let's see. Yeah, now you can see that this is the f square curve, right? This is the f square curve. Here I am taking 3.5. okay, let's not 3, here 4 solution is there, so let's 3.2 maybe. Yeah, 3.2 is also 4 solution. The 4 solution, why I am saying the 4 solution, it is nothing but because here one solution, here there is a one solution, because here the y equal to x cut the graph once, then here, then here, then here. So this 0 point is obvious, because if I put here it is trivial solution of this equation, because if I put x equal to 0 here, so left side becomes 0 and right side also becomes 0, so that is obviously a solution. Then there is a two solution, there is a third solution, and third solution, one thing I want to say here, why there is a fourth solution. So let me think in this way, that suppose there is a point x0 which is a fixed point of f, then what equation it will satisfy, that then it will satisfy, since x0 is fixed point of f, then it says that it will remain fixed under the action f. Now if I apply another f again, another f on f of x0, so that will say f of x0. So since f of x0 will remain x0 from the definition of this fixed point, then it will say that f square x0 will be x0. So you see, any this is a general result, any fixed point, any fixed point of f, so any fixed point of f will be two period as well, because since it's remain constant under the action of f, remain fixed under the action of f, it will also remain fixed under the application of f square. So that's why you will get these 2 points, 0 and this point will be 0 and this middle point actually. So 0 and this middle point represent that these two fixed points are corresponding to the fixed point of f, and these two fixed points, these and these two fixed points are corresponding to the fixed point of f square, which is not fixed point of f. So there could be any other things like that, there could be, so if I say it graphically it will be more clear, maybe. So suppose there is x0, so if I repeat 1 times it will go back here. Now if I think if I repeat 2 times, 1 times and 2 times, then also it will again come back to same. If I repeat it 4 times, it also came back to the same point. So I can think the 1 point orbit as 2 point orbit, 3 point orbit, 4 point orbit, so many. But there could be possibly another thing also possible, that there is a 2 point, so first is going here and second is going here. So this is also 2 period orbit. So I am saying this 0 and this middle point corresponding to the fixed point of this first kind. So this is x equal to 0 and x equal to middle is this kind of fixed point. Now it's in the second and fourth, these two fixed points, second and fourth, these two fixed points are second kind of fixed point. Now these two fixed points actually corresponding to, if I go back to this card, so these two fixed points are corresponding to this point, and okay, the one is this point and another is this point. So one is this point, another is suppose one is this point, another is this point. So these 2 points are corresponding, these 2 points are this and this. So its value is, if you see here, its value is one is 0, then one is 0.51 and another is 0.68. That's it. Now let's see another thing, that okay, that's all. That's how you will see solve the equation. Let me give another example where it will be pretty much clearer. So suppose for where I can use where the number will be very simpler, so that's why it is easier to see. Let's see. So an example is, suppose f is a map which maps R to R, and the map is fx equal to x square minus 2. We have solved this equation previously. So how this first of all, since it is very easier to first of all let us calculate what will be the fixed point of f or 1 point periodic orbit of f. So 1 point periodic orbit means only by application once of x0 it will remain x0. So this is the 1 point periodic orbit. So if I apply this x0 square minus 2, it will become x0. Now this means if I solve this equation, x0 minus plus 2 will be 0. So this is x0 square minus 2x0 plus x0 plus 2 equal to 0. So this will be x0 minus 2 plus x0. Okay, I think something is wrong here, so it will be minus. It will be minus. Thank you. It will be minus. So then this is x0 minus 2 will be 0. So this is x0 plus 1, x0 minus 2 equal to 0. So this is x0 equal to minus 1 and x0 equal to 2 will be the solution. Let's see first in the using also computer whether it is same or not. So we have to change the function. So function is fx is x square minus 2. Now this is right. Now we have to see that thing. Okay, now we have to plot only fx, since we are not seeing the 2 period orbit, we have only want to see the 1 period orbit. Okay, I have to minus this is from 0 to 1. I have to take account of maybe minus 4 to plus 4. Let me take into account minus 4 to plus 4. Minus 4 to plus 4 or minus 3 to plus 3. Because the two of the solution what we have calculated, one is minus 1, one is 2. Both of the solution are out of our previous range. Our previous range was 0 to 1, because now let's see. Okay, now it is pretty clear. There are two solutions. One is nearer here, another is here. So if I click here in this point, you can see this is minus 1 and this point is 2. Here you can see the coordinate in the right side of the bottom of this panel. You can see the coordinate where my cursor is touching. So this is the point. So you can see this point is 2. So 2 is the solution and there is a minus 1. This is minus 1. So minus 1 is the solution. So now we know that there is two solution and that is matching with our calculation. So it is right. Then let's see whether what is the solution of f square. Means is first we calculate the first 1 point orbit. Now we want to calculate the second point orbit. So second point orbit will be remain same under the action of f square x0. So that will be x0. So from our previous knowledge, we know that since these two points, since these 2 points are one point orbit, so if I apply 2 times f here, it will remain x0. So these 2 points should appear here also. Since this is a one point orbit, so since this is a one point orbit, so it look like under the f, it will return back to this point again. So if I apply 2 times f on the same point, it will again come back to that same point. So this is as well as 2 orbit also. So that's why we will get these 2 solution, and with that we will get another 2 solution. That 2 solution will be corresponding to this kind of solution. So first x0 to x1, then x1 to x2. So this will be, so first of all, f of x0 will mean fx0 will mean it will mean f of x0 its square minus 2, and f of x0 will mean x square minus 2 its square minus 2. So it will become x to the power 4 minus 2x square plus 4 minus 2. So it will look like x to the power 4 minus 2x square, x plus 2. Now we have to solve these equations. We know the right hand side how it looks like. So it looks like x to the power 4 minus 2x square plus 2, and I have to solve it is equal to x. So this is the equation you have to solve. X to the power 4 minus 2x square minus x plus 2 equal to 0. So obviously you can see one solution. One is that we know that one solution is 2, right? Because we know that from our previous knowledge, we know that this will be a solution, because this will anyway come back to the same point under the if I repeatedly apply 2 times it. So this will be solution, and indeed it is. So if I see, if I take x square from here, it will become x square minus 2. Okay, so minus 1. This will be x minus 2. No, it is not look like this. So maybe I am wrong here. So that's why I am not getting the point. So here you see here the point is, it is not minus 2. X square minus 2 its whole square means x square minus 2 into 2 into x. So it should be 4x square, because it should be 4x square, because 2 into x square, so that will be 4x square. So it should be 4. It should be 4. It should be 4. This will be 4. So this is x square. This will be x square minus 4 means x minus 2 into x plus 2 minus 1 into x minus 2 equal to 0. So if I take x square minus 2 common, so x square minus 2, this will be x square x plus 2 minus 1 equal to 0. So you see here that this is x equal to 2. If x equal to 2 is 0, the whole is 0. So x equal to 2 is a solution, that we know. Another is x square, that this becomes x cube plus 2x square minus 1 equal to 0. Okay, another thing is the solution is minus 1 is also a solution. If I put minus 1 here, you see, if I put minus 1 here, minus 1 cube means minus 1 plus 2x square means 1 and minus 1, it will be 0. So minus 1 is another solution. So let me do it. So here how I will do it, I don't know. So okay, let's see. See if cube minus I put x square in this way, then I have to take okay, don't think too much. So it is hard to solve. So let's we know that x equal to 2 and x equal to minus 1 is two solution. Now there are another two solution exist. For that we have to solve this equation, this cubic equation, and cubic equation, to solve a cubic equation is not straightforward. We can do it in principle, but it is not straightforward. So let's go back to our graphical method to see that whether or not we can solve it. Or so first of all, change these to f of x. Now we again here I have to change f of x. Okay. Let's see whether it, yeah, you see now I don't want to. Let's solve for minus 2 to plus 2. Okay, minus 2 to plus 2, minus 2 to plus 2. Okay, now you see here we can see that minus 1 should be a solution. So you can see this point is corresponding to minus 1, so this is a solution, and plus 2 is a solution. Now another two solution is popping up here. So one is this point, so this is minus 1.6, this is also a solution, and this is maybe 0.06, yeah, this is corresponding to 0.06, this is also solution. So you know here that there are four solutions, the two solution corresponding to the one period orbit, and another two, which is one is minus 1.6 and another is equal to 0.6. These two will be two period orbit. These two fixed point is nothing but minus 1.6. If I draw minus 1.6 and 0.6 along the x-axis, here, suppose this is 0 somewhere, so this point is minus 1.6, this point is 0.6 suppose. So you see under the action f, 1.6 will go to here, and under the action f, 0.6 will go to minus 1.6. So that's why it is two period orbit. Is it clear, Subhusaji? No, 1000 iteration means 1000 means I am just taking 1000 values of x. So I am taking the 1000 values of x. So I taking first 0, then 0.001, then 0.002. So you see up to 1. So it will I am saying that taking 1000 points in between 0 to 1 uniformly. That 1000 means. So by using this x, using this x, I will draw this every point. So I will put x in f square x. I will get a point here, and then here, then here. That's why I will draw the curve. It's not iteration. I am here. Here there is no iteration. I am only solve for the fixed points by using map. So this was one thing to show that by using map we can solve the equations. Now let's go to the thing that asymptotic periodic orbit. Not asymptotically, it's called it's appear periodic, but it's not actually periodic. So why I am interested in this, because it shares so many properties with chaos, but it is not chaos. It is shared two properties, at least two properties of the chaos. One is it is space filling, means if I this type of behavior, if some system shows dynamical behavior, if some system shows, you will see like the chaos, it will go everywhere in the space, and it will never stop to a fixed point. In fact, this system has no fixed points. Another thing is what is not what property is not there in that in quasi-periodicity is that the sensitive dependence of the initial conditions. So that's why I am interested to show you that there exists a periodicity, or it is called quasi-periodicity. It's being called quasi-periodicity because that it is periodic but not quite in the same way as we have seen here. So it is called quasi-periodicity. Quasi-periodicity. So to introduce, and I only introduce quasi-periodicity because it will appear if you go through there is a part in physics which is called classical physics. So there is a thing called Hamiltonian chaos. So there is called Hamiltonian chaos. So there you see that this quasi-periodicity will appear much more organically than here, because here I just want to show you that there exists some other thing other than periodicity which looks like chaos but it's not, which shares some properties. So two properties will share. One is transitivity and obviously periodicity. One property holds, but it will not hold this property, that sensitive dependence of initial conditions. So this property it will not hold. So it's fun to see. So to see the quasi-periodicity, we need two-dimensional coordinate. So suppose we have two coordinate. Suppose our space is previously our space was one coordinate because only x was there. Now, and the oscillation was going on, or period is going on, or oscillation is going on x-axis, only x-axis. Now suppose that there is now our space is x and y. So x and y. So a point here is denoted by x comma y, and oscillation means both x has to return to this value. So suppose that let me take this grid. So suppose x return to its value. Suppose since x is same here and here, another draw. Suppose x has returned to its initial value. So since x is same here, but y is not returned to its this value, it will take this point, because y does not go back to here, y suppose is this much, so the whole system will not go to this point, it will go to this point. So is it clear, Sobusaji? So in the let me again explain it. So in the two-dimensional oscillation or two-dimensional oscillation, since there are two coordinates, so to say that it completely came back to its initial position, that's it's called the oscillation or periodicity. Then we have to say that we have to check that whether x and y simultaneously come to this point. If x come to this point but y does not come to this point, we will get any point in this line, and when y also came back to this point, we will get exactly this point. So this is important to understand the quasi periodicity. Is it clear, Subhasaji? Okay. Oh, okay, no worry. So transitivity means, if I have a suppose 2D, so if I start from this suppose if I give some time to evolve the system, so at there if I give some system infinite time, then I will say, then transitivity say that if you choose any open subset of this interval, you will get some point of the orbit inside this region. That means that that is mathematical term. So it physically means that your system, your orbit is actually suppose here these points are moving like that from here to here, here to here, here to here. It's saying that this point will go everywhere into this space. Suppose your x belongs to 0 to 1, y also belongs to 0 to 1. Then transitivity says that there if you wait enough, then and if you repeat iteration, your system, if you start from anywhere, it doesn't matter from where you started, but wherever you started, if you wait enough, and you will see this point will going to any open interval of this interval, means it will go everywhere in this space. Transitivity means that. Is it clear? Okay. So let's see now. Suppose now here the comes that x and y can have two different time interval, means different, what I am saying. So different suppose x and y, x0 is evolving through a map f. So we are here getting this kind of thing. Suppose x1 is f of x0, but y1 is g of y0. So there are two different kinds of map which take these 2 points x0 and y0 to another coordinate. These two together will takes these initial positions to another position x1, y1. Now suppose x0 is a m period orbit. Suppose x0 is a m period orbit, and y0 is a n period orbit. This kind of thing. That means after mth time, means after mth generation, you can see the two coordinate system like prey predator system. Suppose x0 is the population of prey and y0 is the population of predator. So prey are evolving due to other factor, and predator also evolving due to another factor. And after one generation, you are observing the population density of the prey predator. Now, suppose that this prey, the population of the prey is actually periodic. If you see after mth generation, you will see that the prey population return to its original, means its initial state or initial population size, and predator population, then the predator population will not came to its initial position, but it will came to its initial position after nth period. So that kind of thing. Now we can say this nth period, instead of this we can say that after time t, suppose prey, or maybe t1 t2, suppose after time tx is the time period of x oscillation. So it is after tx time it will return to its original state. And not original means if I observe from somewhere, suppose I am observing from x0 start, and if I wait tx time, it will return to x0. And similarly ty is saying that a time period of y oscillation. This means y is oscillating, but if I observing from, suppose from any y, and if I wait ty time, it will return to its same position. Now let's see from an example. Suppose x equal to 2 and ty equal to 3. After second iteration it came, after third iteration it came. So, or maybe you can write it here in this way, that tx and ty is suppose tx is 2 ty. This means not, since I think 2, so only 2 is needed. I don't know, because this is x, this is y, so y is smaller, x is larger, so maybe 1 is enough here. So it says, so if in the first ty, suppose I started from here, okay, and if I observe from ty time, this state, the y, since if I observe from ty time, y will return to its value, so y will be anywhere in this red line. So the y will be same for this red line, but where the tx reaches, tx is not reaches at the same point. Suppose tx reach to some point, suppose here, so tx reach to this point. Suppose tx reaches to some value in between, so it will look like that. Tx will be means the position of x will be anywhere in this line, so the system state will be here. Now the system state after ty time, since after ty time y came to the same value, because ty is the time period, by x does not came back to the same value. But if I wait after another ty, so then ty will become 2 ty. So if I wait 2 ty, it will return to the same positions here. Again it will return to the same position here, x also. And after ty, since ty it will return, y also return here, and x will also return here. So after ty it will return to the same positions. Now an interesting thing happens. Okay, an interesting thing will happen when we will see. So it's a little bit tricky. So an interesting thing will happen when you will see that this tx will be some multiplication, suppose p ty, but this p will not be a rational number. So don't worry about this. I am only showing you that there exist some other concepts with the chaos, which is look like chaos, but it is not quite like chaos. So p is rational. If p is rational number, then you will see always that system will return to its initial state and it will become a closed orbit. So if you see in the map like things, so if x, suppose it will go here and then it will come back here, so it closes the orbit, so it will become a closed orbit if the p is rational. Whereas interesting thing will happen when the tx will not be, tx will be p ty, but this p is not rational number but irrational number. So as for example, suppose instead of p is 2 ty, suppose p is root 2. Now you can't say that, means you can't represent root 2 in this way, that in any form of irrational number, means you can represent the root 2 in any r by t form. So you can't say that if you can't here for the rational number case, you can write is tx equal to r by t ty, but here that means t time of tx will be r times of ty. You can say here like this. That means if I can iterate rt times, suppose here rt times, here also rt times, then you will see that the system will return to its same position. But here you cannot write it in r by t form. So then you will see that the system will be oscillating, because since we are since x also oscillating, so x will also came here. Okay, let me draw another. So here they will not oscillate, because since we cannot represent it in p by q form. So one time you will see that x will come here, but y does not come here, y will come here. So you will see from, if you start from here, you will see that point will come here and it will never come to this same point, because it is not rational number. That's why you see that the system will not becoming a closed orbit. So let me show you a Python program where I can show you a orbit which is quasi-periodic orbit. So let me clear. So you see this is quite like a it's in the contrary of the chaos. It looks like order, but it is not quite periodic, because it does not return to the red point. It will go through here and there in every point in the space. Now Sobuzaji, do you see that the point that I am saying, that it is space filling curve? You can see it can go every point in the space like the chaotic orbit does, but it is not kind of chaotic. So that is the main thing I want to say here, That's why I said these many things. So is it clear, Subodhaji? I know. Right. Ah. Right. Right. Huh. Hmm. Quasi periodicity. Yeah, it's like for the Earth and the planetary motions, they are like quite quasi periodicity. There you can observe some kind of quasi periodicity. So uh, so I'll show you next time the quasi periodic orbit or something like that. And in nature, other than that, in my mind, I cannot recall any other example other than that. So okay. Okay, I'll try. So, and I am want to say you that in the next Friday there was a class, but I can't able to take that class. So I will see you in the next Monday again. Okay? Ha ha ha. Hmm. Hmm. P by Q form. Right. Yeah, yeah. Hmm. Yeah. No. Yeah, yeah. It is confusing. It was confusing for me, but I corrected myself. You see that we write pi is not equal to 22/7. It is approximately equal to 22/7. You pi is a irrational number. You can't write in 22/7. It is very wrong thing. But you say that we can approximately write it by 22/7. It's not exactly equal to 22/7. So it was a confusing thing, because from our since our childhood where means we learned that pi is equal to 22/7, but it is wrong thing. It is absolutely wrong. Pi is not equal to 22/7 exactly. You can only approximately say that pi equal to 22/7 means only tenth or the up to tenth. I don't know up to how many order the pi will be matching with 22/7, but up to up to 3-4 order 22/7 actually matches with pi. That's why you can in reality you can work with that number instead of pi. Is it clear? Yeah, yeah. Hmm, hmm, hmm. Okay, okay. Yeah. Okay, thank you. You are ready.